Science Alliance, hello. Still got this board's a right mess. This is our last lesson in the solids, liquids and gases module, which is deeply exciting because obviously all of the modules are great, but it means we've only got magnetism and radioactivity and astronomy left, and then we've finished the whole GCSE course, which is ridiculous. So I've just got a bit of I was being a polar bear today for our polar regions lesson. So yeah, we're going to talk, it's probably one of my favourite topics actually. I still remember being taught this when I was teacher training. The Kelvin scale. Let's just do the activity straight away. So you need a narrow-necked bottle. Some of you have done this with me before. It's better if it's made out of glass. If it's made out of plastic, it'll probably still work. You need a little bowl or cup or something of washing up liquid, and a bowl of cold water and a bowl of hot water. And what you've got to do is you've got to dunk the bottle in your washing up liquid mixture so that you get a bubble film over the bottle. Don't do what I'm doing. And hold it really near your very expensive computer. There we go, right. So I've got a bubbly film. And then actually the first thing to do is just hold it. Just hold it in your hands and see what happens. Oh, wow, look, that was fast. Straight away. So can you see that a bubble is growing? Ooh. So you're IGCSEs, right? So I need you to think about why that is happening. I'm hoping, wow, that's really growing actually. We've done a lot of talking about particles this last few weeks. So I'm hoping you'll be able to tell me why there is a bubble now growing out of my glass bottle. What I should have done actually is to leave it for a while to show that it doesn't grow if you're not holding it. But anyway, so that's really nice, isn't it? Maybe you're doing that with me. Now what I'm going to do is I'm going to put it into the... Oh, it's popped. Okay, well that's a good opportunity to see what happens if it doesn't get held. I'm going to put it into the hot water now, and you can do that as well. Oh, it's actually, it is slightly growing, see? It's growing a bit, but hopefully you can see that it's more or less stopped now. We've not got as much growth as when I was holding it in my hands. Let's put it in the really hot water. See what happens. Whoa, look at that. So come on, why is that happening? Wow, that's huge. Beautiful. I love this activity. Cool. Oh, there you go. And what do you think will happen if I put it in the cold water? Come on, one more prediction. So let's get that bubble film again. There we go. So I'm going to put it into this icy water now. What's going to happen? What's going to happen? You got something? You worked it out? Let's see. Oh, it's coming up. Ooh, it's going down again. Oh, that was cool. Oh, brilliant. This didn't work yesterday on Facebook, so I'm very pleased to see it's happening. Look, it's going down. Did you expect that? Is that what you predicted? And why did you predict that? What is happening inside this bottle to make that bubble go up and down? It's still very fast. So I'll put it in the hot water again and see what happens, see if it survives, and then I will get on with the lesson. Put it in the hot water and... Hey, it starts going up again. Brilliant. So can you explain that? It doesn't matter if you can't, because I'm going to help you explain it in a sec. Oh, yes! Sorry, maybe this is a bit boring for you. I'm really enjoying this. Wow. Fantastic. Okay, I guess we better get on with the lesson. So you might be thinking about... Oh, there we go, right. You might be thinking about pressure. Just a little reminder, we've talked about this a few times now. The particles in a solid are rigidly bonded. I keep saying they're still moving around. They're still they're vibrating on the spot. So I suppose they're not moving around, but they are vibrating. They are moving. Liquid particles, they are bonded, but they're moving around each other, kind of like a ball pool. They're actually constantly forming bonds and then breaking bonds, so they're free to move. And the particles in a gas, there's no bonds between the particles at all, right? Are you okay with the idea that particles with more energy move around more? So we've been seeing how if you heat up a solid enough, then those bonds between the particles break down and the particles move around more, and eventually the solid becomes a liquid. And then if you heat up the liquid, eventually those bonds break and the solid becomes a gas. So particles with more energy move around more. And as gas particles gain more and more and more energy, if you kept shifting energy to this gas, the particles would spread further and further apart, or they would try and spread further and further apart. So that's what's happening right inside your bottle, is you've got a bottle of air at a fairly standard room temperature. You put a little bubble film over it. When those particles of air heat up, they get more energy, so they spread out more, so the bubble goes up. And then when you cool the air particles down, the opposite happens, right? They slow down, they move closer together, so the bubble goes down because the air is literally taking up less space in the bottle. So there's fewer air particles pushing up on the bubble. Is that okay? I guess actually, yeah, what you're seeing is air particles when they've got a lot of energy, they're colliding with the bubble film, which is making it go up. And then when you put it in the cold water, there's fewer collisions because the particles are slower. So because there's fewer collisions, the bubble shrinks. Is that right? So we're really talking about pressure here. Pressure is particles kind of bashing against the side of their container, right? So you're experiencing air pressure right now. There are air particles bashing against your body, which is fantastic because if it wasn't for that air pressure, then well, astronauts have experienced it. Like the bubble, the liquid on your tongue would start to like go off into the atmosphere. So it's all good. Just to sort of test how much you've understood this. I was trying to teach pressure in all ages lesson. We were doing the all ages lessons on flight, and like 5-year-olds come and 14-year-olds come, so I try and make it sort of like correct science, but I try and really simplify it. And I lashed out this slide. Can you tell me what ridiculous mistake I've made on this slide? I did the lesson, and then I got to this bit and I was like, oh no. I was trying to teach pressure in the all ages lessons and I lashed out this slide. What silly mistake have I made? This is the slide. Let's talk about pressure. Pressure in liquids and gases is caused by the particles bumping into the sides of the container. And I've got a picture of 2 balloons here. One balloon's got loads of particles in it and it says more bumping equals higher pressure. And the other balloon's got fewer particles in it and it says fewer collisions, lower pressure. What ridiculous mistake have I made there? Oh, I was embarrassed. Oh, how we laughed. If you want a clue, none of the written information on the slide is incorrect. All of the words are fine. So yeah, the mistake that I've made is the balloon would get smaller, wouldn't it? Obviously, the balloon would get smaller. You wouldn't have a balloon that was the same size with fewer particles. The reason the balloon is that size is because of the amount of particles pushing against the side of it. Particles pushing against the side of it, then the balloon would get smaller. Okay, so we're talking about volume today, which is like the amount of space that things take up. And we're talking about pressure. So yeah, we need to start. Oh wow! Oh gosh, sorry. I just got there was some goose poo in Lego Story Show and somehow it has ended up on my computer. So when I showed you this slide a few minutes ago and said there were no bonds between the particles in a gas, I've put as gas particles get more energy, they spread further and further apart. In other words, gases with more energy exert more pressure. Hopefully you're okay with that. So let's talk about temperature. You could actually use your bubble growing out of a bottle as a temperature scale, okay? We don't really think about it, but all the temperatures that humans use, all the numbers like 5 degrees Celsius, 12 Fahrenheit, they're all made up by humans, okay? You could say, all right, when this bottle's really hot, then a big bubble comes out, and I'm going to say that a big bubble means hot, and you could say when the bubble's like down here inside the bottle, that means cold. You could put numbers on it. You could say that big bubble is 10, and when it's down there, that's 0. And then you could say all the bubbles in between are like 1, 2, 3, 4, 5. So you could be like, oh, water for tea, you need to make sure that it's temperature bubble 7, all right? And that would be fine. Like, what does Celsius and Fahrenheit mean? Fahrenheit, we actually have no idea what it means. Honestly, we have no idea. Someone came up with a scale where a Danish person was like, okay, I'm going to say that 0 is just colder than it ever gets in Denmark. And then one big number on the scale was like body temperature, which you can understand. And then someone, Mr. Fahrenheit, got hold of this and like times all numbers. We don't know. Celsius, you probably know, we've talked about. The person who invented the Celsius scale said, okay, I'm going to say that 0 is just when water freezes. They could have used any liquid, obviously, but water is very common on Earth. I'll say that 0 is when water freezes, and 100 is when water boils. And I'll put little divisions in between. But they could have said that water boiling would be 10 and water freezing would be 0, but then you'd only have 10 divisions. So 100's better, it makes it more precise. But yeah, temperature is made up, is what I'm saying, really. And then, finally, a temperature came along that meant something. And this is where we get to talk about pressure and temperature, all right? Are you okay with the temperature? We talked about this last week. Temperature is a measure of how much energy the particles have. So particles with a lot of energy, particles at a high temperature, exert a high pressure, yeah? Lots of collisions. And particles that are cooler are at lower pressure, okay? There's fewer collisions, right? So you could draw a graph of that. Don't worry, I'm not going to make you do it. But here is what it would look like. We've got pressure going up on the y-axis, temperature going across on the x-axis. So when the temperature of a gas is really high, then the pressure is really high. And as the temperature gets lower, the pressure is lower. So our graph looks a bit like this. Someone called Robert Boyle, you might have heard of him, like Robert Hooke's mate from the 1600s. He discovered this. Now, obviously, the pressure of a gas at 0 degrees, or the pressure of anything at 0 degrees isn't 0. There's always a little bit of pressure. It was Lord Kelvin came along and was like, looked at this graph and thought, okay, up here, things are very hot. They're moving around a lot. And then they cool down and they start to slow down and they start to slow down and they start to slow down. So Lord Kelvin thought, well, there must be a temperature where things just stop moving completely. And what is that temperature? And you don't even have to do an actual experiment. You can just use maths. You just extend this graph out behind so that now we've got negative temperatures. And you just continue this line, which he did. And it just so happens that the temperature at which all particles would even stop vibrating on the spot, even in solids, they would just be still, is minus 273 degrees Celsius. So what Lord Kelvin did is say, all right, let's call that 0. We'll call that 0 Kelvin after me. Modest chap. So what you'll often get told, you need to remember this for IGCSE, is that this 0 Kelvin, the temperature at which all particles just stop moving, is absolute 0, it's called. Nothing can be colder. There's no minus Kelvin. There actually is. You can look it up if you're interested, but there is minus Kelvin. It's really weird. I don't understand it. I'm not going to talk about it now as far as you're concerned. If you're doing IGCSE physics, absolute 0 is the temperature at which particles just stop moving. We haven't ever recreated it in a lab. We don't know of it happening. Even space is 3 Kelvin. Don't say 3 degrees Kelvin. That's not a thing. It's just 3 Kelvin, okay, roughly, space. We haven't got anything particles to stop moving at all, but it's a cool idea. So this is where the Kelvin scale comes from. And this is generally what physicists use. So you need to be able to convert from degrees Celsius to the Kelvin scale. There's a really simple little formula, but I find it quite confusing. I'm going to show you this number line and see if you can fill in any of the gaps on this number line, and then I'll tell you the formula, okay? Oh, look, there's some more goose poo there. Yeah, here we go. So I've given you a number line of degrees Celsius and a number line underneath it of Kelvin. There's 0 degrees Celsius in the middle, and then underneath there's just a blank space. So if it's something 0 degrees Celsius, what would it be in Kelvin? Right at the far end here, we've got 0 Kelvin is the same as minus 273 degrees. Is that okay? Are you getting this? So particles slow down the cooler they get, and when they're so cold, that's minus 273 degrees. But obviously that doesn't really mean anything because the whole Celsius scale is just based on water. So Kelvin said, right, we'll just say that that's 0 instead. So 0 Kelvin is minus 273 degrees Celsius. They're the same. So I've got 10 Kelvin here. what is the temperature in degrees Celsius that is the same as 10 Kelvin? And then if you're feeling really ambitious, I've got 400 Kelvin here. What's the temperature in degrees Celsius that is 400 Kelvin? I was very pleased with this on Facebook because loads of people were getting it wrong. And one person gave me all three answers straight away and went, easy! And I was like, oh, nice one. You got the last one wrong. So don't worry, if you're really struggling with this, then I've sort of the idea. I'll give you a clue in a minute, but just have a stare at it, see how many you can fill in. Important information, 1 Kelvin is the same size division as 1 degree Celsius, right? So the same amount of marks on the degrees Celsius scale, they will be on the Kelvin scale as well, which is nicer, isn't it? Makes it easier. I will give you a clue in 10 seconds. Okay, your clue is, if you look at this degrees Celsius scale, it's minus 273 at the end, and then it goes up to 0. So you know that space along that line there are 273 degrees, right? Between minus 273 and 0 are 273 degrees, and that's your clue. Okay, are you ready? Let's have a look. So if there's 273 between minus 273 and 0, then you just add 273 onto 0 Kelvin, right? To get what it equals in what the equivalent is to 0 Celsius. So 0 degrees Celsius is 273 degrees. Well done if you got that. I think it's quite hard to see that. Sorry, 273 Kelvin. Is that right? The next one, yeah, you have to be really careful here because you're adding on 10 to the degrees Celsius scale to get the new degrees Celsius, right? So 10 Kelvin is minus 273 plus 10, but it's minus numbers. So minus 273 plus 10 is actually minus 263. A lot of people on Facebook were saying minus 283, but is that all right? When you're adding to minus numbers, the number actually gets sort of, it's like, it goes, I was going to say it gets smaller. You know what I mean? Like it gets further, this number's kind of got to get smaller and smaller as it gets towards 0. And here, well, you had to spot that between 273 Kelvin and 400 Kelvin is 127. So if you do 0 plus 127, you should have got, it's done that thing again, hasn't it? Bleep, 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 bleep. 400 Kelvin equals 127 degrees Celsius. Here are the formula. The temperature in degrees Celsius is the temperature in Kelvin minus 273. the temperature in degrees Celsius is the temperature in Kelvin minus 273. That works, doesn't it? So 0 degrees Kelvin, 0 degrees Celsius is 273 Kelvin minus 273, which is 0. And the temperature in Kelvin is the temperature in degrees Celsius plus 273. It just depends how your brain works. I hear that and I just hear blah, 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 blah. I would have to draw this little number line if I was in an exam, but it's entirely up to you. You might find that properly intuitive. Okay, right. So we learned specific heat capacity very recently, and I said, well, this is the hardest equation that you'll get at IGCSE physics. It wasn't. This one I think is more complicated. We're going to do the ideal gas equation. I know, exciting, right? What is an ideal gas? You hear this phrase all the time in physics. An ideal gas is one where the particles don't interact at all and it behaves exactly as you would expect it to. It's hypothetical. It does not exist in real life, but physicists love imagining that things are perfect because it just makes the maths easier. It just makes the equations easier, right? So an ideal gas is just one where there's no funny business, there's no collisions between the particles. We'll just pretend it's a perfect gas where all the particles are not bonded together, okay? So in an ideal gas, pressure times volume equals a constant. What does that mean? Well, I'll show you. I mean, you quite possibly know this already. If something is a constant, so let's take 6 times 2. 6 times 2 equals 12, okay? If we want this number to stay 12, right? If we need this number to stay the same, but we want to play with these numbers, what do we do? Well, if we double the 6, then that would be 12. So we want this 12 to, we have to have this the same. So if we double the 6, what do we have to do to this number? We have to halve it. Is that okay? If you times that number by 2, but you divide that number by 2, then the sum still works and you still get 12. If you times that number by 2, then you could, if you times that number by 3 and divide that number by 3, then you still get the same number. I feel like I might be making things more complicated. But what I'm trying to tell you is that let's just picture a gas, an ideal gas, in a very big box, all right? It's a big box, so it's got a big volume. But the gas inside, because it's got lots of space, it's not at a very high pressure. It's not colliding very often with the sides of the box. So a big volume means a small pressure, not many collisions on the side, right? If you blew up a balloon, well, I'm not going to get into it. Imagine that I squish that box. So I make the volume small. What have I done to the pressure? Well, if there's the same amount of gas particles in, but suddenly they're in a much smaller volume, then the pressure goes up, right? They'd be bashing against the sides of the container a lot more. And it just turns out that if you half the volume, then you double the pressure, all right? Forget about that. This is easier to picture, I think. You've got a gas in a big box. It's at a low pressure. If I half the volume, then I double the pressure. Is that okay? If I make the volume a third, then third smaller, then the pressure is a third bigger, okay? So kind of like this, I guess. If you times the volume by the pressure, you always get the same number, okay? The pressure times the number, because one goes up and the other goes down at the same time. The result of timesing them together is always the same, which is what I mean by, in an ideal gas, pressure times volume equals constant, because when the pressure goes up, the volume goes down. And here's a picture that I found for free on the internet that kind of shows you what's happening. So you've got P here, which is pressure. You've got a volume of gas here. And when you push down, you halve the volume. That's V divided by 2 because it's been halved. So what happens to the pressure is it times this by 2. Okay? If you have a cylinder of air particles and you squish them, the pressure times the volume at the beginning, so just P times V, that's it at the beginning, would be the same as the pressure times volume at the end. So 2P times half V still works out as P times V. pressure is doubled, but volume is halved. So just like with the 6 times 2 equals 12 thing, the result is the same if you times them together. Whew. In other freaky physics words, okay, this is the last thing we're doing on this module, little p1 v1 equals little p2 v2. This is our equation for today that we've been warming up to, where p1 is the pressure at the start, v1 is the volume at the end, at the start, p2 is the pressure at the end, and v2 is the volume at the end. Whew, let's just have 3 questions, okay? Let's see how we get on with these. And then we'll call it a day on solids, liquids and gases. So for example, and here's a little picture to try and help. Question 1, a gas has a volume of 40 centimetres cubed, right? That's its first volume, that's the volume that we're starting out with. A gas has got a volume of 40 centimetres cubed, and it's got a pressure of 10,000 pascals. It doesn't actually matter if you can't remember anything about pressure, just accept that pascals is the unit of pressure. So that's the first pressure, 10,000 pascals, and that's P1, and 40 centimetres cubed is V1. If it is compressed, squished, so that suddenly the volume is 20 centimetres cubed, so V2 is 20 centimetres cubed, what is the new pressure? I can hear some of you freaking out. Don't freak out. I'll show you on the board. So we've been talking a little bit about how to rearrange equations in a very lazy, not very explainy way. Are you okay with the fact that P1 V1 means P1 times V1? The pressure at the beginning times the volume at the beginning. And this is the pressure at the end times the volume at the end. So in this question, you're looking for the new pressure. So you're looking for P2. So we've been saying, if you're looking for P2, you need this sum to say P2 equals blah, 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 blah. So you want to get rid of V2 from this side. And because you've timesed on that side, if you move it over here, you just do the opposite. I don't think maths teachers would be very happy with this explanation, but you can, if you're timesing by V2 on this side, you can divide by V2 on that side, and then that V2 cancels out. So we are left with P2 equals P1 times V1 divided by V2. Have a go. How are you getting on? It's absolutely impossible to tell whether you're all like panicking to get finished or whether you're all sitting there really bored. So, give me 10 seconds. Maybe 20. I'll give you 20. I should have said, sorry, you don't have to worry about converting. I really should have said that. Because as long as you're using, say this is centimetres cubed, you don't need to change it into metres cubed like we sometimes do, because it just, as long as you know that the answer you get will also be in that unit. So if your first volume is in centimetres cubed and you're trying to find the second volume, then that will also be in centimetres cubed. So you just need to write the right unit down. If they gave you a question and they'd use different units, that would be evil. You'd have to make sure you put the same units in, but as long as they're the same, it's okay. All right then, let's go through it, because I will certainly be giving you plenty of past paper questions on this for homework, so you don't need to worry too much if you haven't finished. A gas has a volume of 40 centimetres cubed and a pressure of 10,000 pascals. So that's our first volume and our first pressure. If it's compressed to a second volume of 20 centimetres cubed, what's the new pressure? So we've got this equation and we need to know the new pressure. So P2 we're looking for. So if we divide by P2 on that side, we can get rid of that P2, okay? We'll just move it over there, do the opposite of what's happening on this side. So that's our equation that we need. P2 equals P1 V1 divided by V2. And then, we just don't want to sound cocky, but we can just plug the numbers in. So P1 is 10,000 pascals. V1 is 40 centimetres cubed. And the second volume is 20 centimetres cubed. So you should have got 20,000 pascals is what P2 is. 20,000 pascals. And I would always check my answer, because actually I made a mistake in question 2 when I was working through them. So the new pressure is higher than the first pressure, which makes sense, doesn't it? Because it says we've compressed it. So if you squish a gas, you do end up with more collisions, so the pressure would be higher. Some of you will have just been able to look at this and think, oh, the volume's halved, and therefore the pressure must have doubled. But, you know, hopefully you practiced using the equation. All right, next one. The gas is compressed further, this is the one I made a mistake on, to a volume of 18 centimetres cubed. What is the new pressure? So be really careful here. We've still got the same, the first volume is still 40 centimetres cubed, and the first pressure is still 10,000 pascals. This is just a different new volume. So we do exactly what we did before, rearrange the equation, because we're still looking for the new pressure. And the only thing that's changing is that the new volume is now 18 centimetres cubed instead of 20. So just put that into your calculator and you should get 22,222.22222. I ended up with I'd accidentally put 18 here. So I ended up with a higher pressure and was like, hey, with a lower pressure, and thought, well, that can't be right, because if you squeeze a gas, you don't make it have a lower pressure. So then I realised what I'd done. So yeah, 22,222.22222. And finally, a gas with a volume of 1 metre cubed at a pressure of 100 kilopascals is expanded until it has a pressure of only 0.75 kilopascals. What's the new volume of the gas? So the gas has been expanded. It's at a lower pressure now, so we're expecting this new volume to be bigger. Right, so we're looking for P2. So we've got to get rid of this P. We're looking for V2, beg your pardon. We're looking for the new volume. So we need to get rid of this P2. So we're times doing on this side, so we'll divide it on that side. There we go. V2 equals P1 V1 divided by V2. So it's 100 kilopascals times 1 metre cubed divided by the second pressure, which is 0.75 kilopascals, gives you V2. And that is 133.33. What's the unit? Be super careful. You've got to always check this or it gets really confusing. What's the new unit going to be? We're looking for a volume, and the unit that went in was meters cubed. So it is going to be meters cubed as well. Phew! Right. So thus ends our module on solids, liquids and gases. She says, realising that she hasn't yet. No, I'll just put it in your homework. I'll put it in your homework. We've missed like a tiny little thing. It's not worth doing a whole lesson on. I want to get on to magnetism. That's what we're doing next week. So if you're new, you're probably not new because that was like the very last lesson in a module. So you will probably have found that incredibly confusing. If you are new, next week is a really good time to join because we're starting a whole new module. So hopefully everyone will be at, well, you're all at different levels, aren't you? But at least as far as I'm concerned, you'll all have the same amount of information from me. So yeah, magnetism, which I think is going to be a really short module, radioactivity, and then astronomy. And then that's it. Jobs are good. And is that Joaria who's here? Or Ryder? Let's have a look. So when I'm live on YouTube, I always put a post on Facebook saying, say hello here if you're watching live, because you can't have comments on YouTube. So I'm just going over to my Facebook page to see if anyone said hello. Oh, they have. Joaria and it is Joaria. Hello, and Tiger and Bird. Oh, thanks for watching, you lot. And thank you to all the people who are not commenting, but are here. Yeah, it's very much appreciated. I always say, if it weren't for that number in the corner showing me that people were watching, I would literally just go make a cup of tea and think, oh, I'll do it later. And then I'd never do it, and then I wouldn't have a job. So many, many thanks for joining me. If you are new, you can go to my About section on YouTube and click the sign up button. There's a link to this website called Coffee, which is how I am doing this completely for free. All of my lessons are free. The printouts are free. If you find my Facebook group, there is going to be a homework PDF in there quite soon with some past paper questions in that I think you should be able to answer after this lesson, and that keeps being updated as well. So yes, thank you very much for joining me. Thank you so much for all the support. It is hugely appreciated. I'll see you all next week for the start of magnetism. I'll advertise that lesson soon on my Facebook page and on my new website as well. All right, see you soon, you lot. Thanks so much for coming. One quick refresh just to make sure that Joaria or Tiger and Bird haven't said anything else, haven't asked any questions, no complaints. No, good. All right, excellent. I'll take that as a good sign. See you soon, you lot. Bye.